Hello, Earth scientists. I wanted to walk you guys through some radiometric dating practice problems. I would suggest you guys try attempting these problems on your own and use this video to help correct your work or figure out how to solve these problems correctly. So you can watch a video, pause it, try to attempt it yourself, and use this to make sure you know how to do the math. So let's start by talking about these diagrams up at the top here. In this first chart, we see different isotopes and the rate at which they decay. So the half-lives, the amount of time it takes for that isotope to decay by half. And in this diagram, the graph allows us to understand the relationship between the percent of the parent isotope in a sample and how many half-lives have occurred. So if we see a sample that has 50% of the remaining parent isotope, we would read the y-axis first and say, here's our 50%, and we would see where that intersects with our curve, our line, and then we would go down to the x-axis to see that one half-life has occurred. If we have a sample that has, let's say, about 25% of the parent isotope remaining, we would approach it where we would find this line and see where it intersects with the curve, and then go down and see two half-lives have occurred if 25% remain. So this is a graph we're going to keep using throughout the practice here. So let's get started with number one. If a sample contains 100 grams of a radioactive isotope, how much would be left after 3 half-lives? So there are a number of ways in which you can set up and solve these problems mathematically. I'm going to show you one approach where we are dividing by 2. So if we're starting with 100 grams and we want to figure out how much is left after 3 half-lives, we would half this sample 3 times. So essentially I need to take this number, divide it by 2, divide it by 2 again, and divide by 2 a third time in order to figure out what remains. So let's take our 100 grams, divide by 2 to show that after 1 half-life, 50 grams would remain. So that was after 1 half-life. Then we would say that this 50 grams would undergo a second half-life, divide by 2 again, to show that 25 grams would remain after the second half-life. And finally, the third half-life would take this 25 grams divided by 2, and we would have 12.5 grams remain after the third half-life. So our best answer would be down here, 25 grams of our sample would remain after 3 half-lives have passed. So let's do number 2. Get rid of that. So number 2 is asking, if a sample contains 50 grams of a radioactive isotope, how much would be left after 2 half-lives? So we're going to take this 50 grams and half it 2 times. So 50 divided by 2, 25 grams would be left after 1 half-life. Then that 25 grams would half again in the second half-life. So we would end up with 12.5 grams. Great job. Let's do number 3. If a sample contains 20 grams of an isotope that has a half-life of 1,000 years, how much would be left after 2,000 years? So a way in which I like to approach this problem is first figure out how many half-lives have passed. We know that a single half-life, 1 half-life, is equivalent to 1,000 years. And this question is asking how much of the sample would remain after 2,000 years. So you could probably do this math in your head, but it's good practice when we get to more advanced problems to show your work. So if we want to know how many half-lives occur over the course of 2,000 years, you would do 2,000 divided by a single half-life, which is 1,000. So you would get 2 half-lives. would have to pass if we're talking about this length of time, 2,000. So now let's show our work and see what would happen to this 20 grams of our sample if 2 half-lives pass. We have 20 grams, and we're going to half it to show that after 1 half-life, 10 grams remain. And then we're going to half it again to show after that second half-life, 5 grams remain. So our best answer would be right here, 5 grams. Great job. Let's do number 4. If a sample only has 20 grams remaining after 3 half-lives, how much was there to start with? So this is what remains after 3 half-lives. So we kind of have to work backwards in a sense. And instead of having our quantity, we need to multiply it because we're going backwards. So this is what remains. So if we had 20 grams at the end of our 3rd half-life, so we would take 20 grams and multiply it by 2 to figure out what we started with at the beginning of this 3rd half-life, which would be 40. So now we're going to take this 40 and multiply it by 2 again. Again, we're working backwards to see what we started with at the beginning of each of these half-lives. So 40 times 2 would be 80 grams. And we would multiply this one more time. 80 times 2 would give us our starting quantity, what we had at the beginning of the 1st half-life or at the beginning, which would be 160 grams. Great job. Let's move on to number 5. If you start with 1,000 carbon-14 atoms, how much remain after 4 half-lives? So we need to divide 1,000 grams in half 4 times. So let's write out our work. 1,000 grams divided by 2 gives us 500 grams after the 1st half-life. 500 grams divided by 2 would give us 250 grams after the 2nd half-life. 250 grams divided by 2 would give us 125 grams at the end of the 3rd half-life. And then we're going to divide this one more time by 2 to find that we would have 62.5 grams at the end of the 4th half-life. So that would be our answer. Number 6, assume you start with 10,000 carbon-14 atoms. Which of the following statements is true? After 2 half-lives, there would be 5,000 carbon-14 atoms remaining. Well, let's see if we can show our work to figure that out. 10,000 carbon-14 atoms are going to undergo some radioactive decay. After 1 half-life divided by 2, we would have 5,000 carbon-14 atoms remain after 1 half-life. So we already know that this first option is not true because this is the quantity of carbon-14 atoms that remain after 1 half-life. So we can get rid of this option. We can also get rid of the second option. After 1 half-life, 250 carbon-14 atoms remain. We see that's not the case already in our math, so we can get rid of that as well. After 3 half-lives, there would be 2,500 carbon-14 atoms remaining. Let's see if that's true. After the 1st half-life, we have 5,000 remain. If that halves again, we'd have 2,500 atoms remain at the end of the 2nd half-life. And if this were to undergo a 3rd half-life, we would see there would be 1,250 left after 3 half-lives. So we know that after 3, this quantity would not be 2,500. So we get rid of that. And let's show our work to show that after 4 half-lives, we would have 625. We see that's true if we divide 1,250 by 2. We would get our 625 carbon-14 atoms after 4 half-lives. So that would be our correct answer. Great job. Let's move on to number 7. What's the half-life of potassium-40? So for this, we have to look it up. So let's use our chart that shows us the potassium isotope and its rate of decay measured in half-life. So it takes 1.3 billion years for it to undergo a single half-life. So that's our answer, 1.3 billion years. We're going to need this value to solve for our next problem. So let's see, number 8. If a fossil originally contained 100,000 potassium-40 atoms and it now contains only 12,500, how old is the fossil? So there are a number of ways in which you can solve this problem. We can see how these two numbers are related to each other. We can do 1,000 divided by 12,500. If you do this on your calculator, you would get 3. So that shows us that 3 half-lives have passed in order for us to get from 100,000 atoms down to 12,500. You could also show your work and show that you would be dividing this quantity by 2 3 different times. So that's its first half-life. Divided by 2 again would give us what's left after the second half-life. And divided by 2 again would give us what remains after the third half-life, which is our quantity, 12,500. So we know that 3 half-lives, 1, 2, 3 half-lives have occurred. We also know that 1 half-life of potassium-40 is 1.3 billion years. So if each of these stretches is 1.3 billion years, we need to take 1.3 billion and multiply it by 3. So 1.3 billion multiplied by 3 would give us 3.9 billion years. So that would be our best answer. Let's move on to number 9. What is the half-life of the element in the picture? Here we have an image. We see that originally it is 100% of some element, and after a period of time, it decays so that only half of it remains. So this stretch of time would be our half-life. How much time does it take for a sample to decay by half? So we see our time is measured in minutes here. So it would be 10 minutes for a single half-life. Every 10 minutes it decreases by half. So this sample then decreases by half after 10 minutes. This decreases by half in another 10 minutes, and so on. So let's keep referencing this image in our next question, number 10. If you start with 100 grams, how much do you have after 30 minutes? So again, we have 30 minutes. You might be able to do this in your head, but know that you can calculate how many half-lives have occurred if you take the total time divided by the length of a single half-life. You would see that 3 half-lives have to occur over the course of this 30 minutes. So if you start with 100 grams, we need to divide this by 2 3 times. So 50 grams would remain after 1 half-life. 25 grams would remain after 2 half-lives. And 12.5 grams would remain after 3 half-lives. So that would be our correct answer. Number 11 says, if you have 10 grams at 20 minutes, how much did you start with? Let's use this different color. So here we have to work backwards. We have 10 grams at the end of 20 minutes. Let's figure out how many half-lives we're dealing with. 20 minutes divided by a single half-life of 10 minutes shows that we're dealing with 2 half-lives. So we need to multiply this quantity by 2 to go backwards, right? What did we have originally? So 10 grams times 2 will show us how much we had at the beginning of our second half-life. 10 times 2 would be 20 grams. We would multiply 20 grams by 2 one more time to figure out what we had at the beginning of the first half-life. So at the beginning, we must have had 40 grams. Great job. Number 12, what percent of the original carbon-14 remains in a sample after 11,460 years? So for this one, we need to use the chart in order to figure out how many half-lives have passed, and then we can determine the percentage from there. So let's go back to the diagram at the beginning of our worksheet. Here we know that carbon-14 has a half-life of 5,730 years. So let's hang on to that number. One half-life equals 5,730 years. We want to know how many half-lives have occurred if 11,460 years has passed. So let's take that quantity and divide it by the length of a single half-life. And if you divide these numbers out, you'll see that 2 half-lives have occurred. So if we're dealing with percentages, we know at the beginning we must have 100% of our sample. And then over the course of time, it decays. So let's figure out how much would remain after 2 half-lives. 100 divided by 2 would give us 50% at the end of one half-life. That 50% would decay again into 25% at the end of the second half-life. We could also find this information in our graph on the front. So let me show you where that is. 25% would be our correct answer. And we would find that by saying, well, we know 2 half-lives have occurred. We would find the point where it intersects in the curve, and then we would go over to the y-axis and find that 25% of our sample would remain if 2 half-lives have passed. Great job. Couple more problems. Let's move on to number 13. How many half-lives have passed to yield or produce a sample with 125 carbon-14 atoms and 375 atoms of nitrogen-14? So let's write these quantities out. We know that we have 125 carbon-14 atoms and 375 nitrogen-14 atoms. We know that carbon decays into nitrogen. So this would be our parent isotope, and this would be our daughter. Let's first figure out how many total atoms we're dealing with. Let's add these numbers up. So 125 plus 375 would be 500 atoms in total. In order to figure out the age of the sample, let's figure out the percent of the parent that remains. So what percent would be this portion over the total? The portion we're talking about is the parent isotope, so the 125 carbon-14 atoms over the total number of atoms. In order to record this as a percentage, we would want to find this fraction, this portion, multiply it by 100. So do this math. When you multiply this out, you'll find that 25% is your answer. So now let's use our graph and figure out how many half-lives have occurred if 25% of the parent remains. So let's clear up our graph. We're looking on the graph, if 25% of the parent isotope remains, that intersects with our curve right here, which means that 2 half-lives must have occurred to cause a sample to only have 25% of that parent isotope remaining. So 2 half-lives. Great job. Last problem, 14. How old is a sample that contains 25% of its original potassium-40 atoms? Well, we just used the graph to show that 25%, that a sample that has 25% of its parent isotope would have to undergone 2 half-lives. Remember our curve, 25% would intersect at a point that corresponds to 2 half-lives. So now we need to figure out how old the sample is if we know that it's the potassium-40 isotope. We know according to the chart at the beginning, potassium-40 has a half-life of 1.3 billion years. So if a single half-life is 1.3 billion years, and we're talking about 2 half-lives, we need to multiply this by 2 to find the age of the sample, which would be 2.6 billion years. Great job, you guys. You guys are awesome. Please reach out if you need help or get stuck. Great job.